This video will help you to understand how the NRG ZONE manifold works and how you can take maximum advantage of the features it provides. For example, from the start you see that it's metal enclosed manifold with different ports or connections to connect boilers and heating system equipment of various sorts. We'll go through that just now. The unit is mounted on the wall by two fixed brackets that can be mounted onto a solid surface. It would be better if it was onto a masonry surface, stone or brick or whatever, but you can of course mount it onto any timber structure, metal structure, but standard pumps which will be attached to it have a very limited amount, but an amount of noise potential, and it would be an idea to put some kind of an acoustic barrier like a little bit of insertion rubber or maybe even tap washers or something behind the manifold, so screws would pass through, catch the manifold, pass through the washers and then adhere to the wall, just to stop any vibration noises. The unit comes completely insulated, and this is a critical part of how the whole thing works, as you'll see in a while. When the unit arrives, all the insulation in place, but it's quite simple to just simply remove the front part. It just pulls directly off, and you can see or any of the parts, so that it's easy for mounting and whatever. Obviously if you're going to mount a unit on the wall, you need to have the back insulation on at the very least, so that you get it properly located before you start to secure it to the wall. Inside the unit it's divided into three separate areas, but as such the top area, being these two chambers, could be classed as one, except this is where flow water would arrive in or be taken from for zones, and this is a bypass back to whatever source the heat might have come from in certain circumstances, but you'll see in a while that's quite easy to grasp when you look at the diagrams that are going to follow. So the top chamber would be regarded as the flow chamber, where flows either enter from a boiler or boilers or go away to a zone or zones. The bypass chamber is where the flow water that hasn't been collected by the zones, which would typically be connected to this pipe here with a pump located here, or the second zone here with a pump located here, or third zone here with a pump located here. This is a 3-zone unit, but of course you can have as many zones as you want, and right down to 2 zones, and in fact there's reason why even 1 zone is a good idea. So the return chamber is different to the other two, because the return chamber receives any water coming back from the heating system having lost temperature, and this is the optimum water for a boiler to work on depending on the level of temperature in the water. For example, a heat pump would need this to make it to get the coldest water to maximize its efficiency. A condensing boiler will need the coldest water to maximize an efficiency. But say for instance you had a solid fuel appliance that might need high temperature water, well this might go back from here because we'll get the returning water mixed as well. So we can see that already the flow from the boiler is used in a very practical way, where it offers itself to the ports available in the flow chamber to be taken away by zones, and then the bypass water goes back to the boiler directly, and so turns the boiler off much sooner than normal, because the return heats immediately with the unused heat, and so heat is available for the zones, but the boiler won't be firing as long. Clearly an energy saving potential. The ports on the left hand side are classed as L1, being the top left hand port, L2 and L3. Just now we're showing that heat might arrive at L1, or it could arrive at L2. If heat arrives at either one of those ports and is pushed through, then this chamber here, the flow chamber, would heat. If the return back to the boiler is going back from L2 or R2, then the water having flowed through will go and bypass and go back to wherever it came from. And same if it comes from this side, it comes around this baffle, travels along the top chamber, flow chamber, down and through the bypass chamber and back. Now, if all the zones are heating, say you have a pump on each of those 3 zones in this example, and a pump was drawing this hot water down and taking away maybe to your underfloor heating or radiant floor system, and this might be doing some radiators, this might be doing some your hot water system, well then the return water would come back on the return ports, and if it comes back on the return ports it collects in the return chamber. This is where it can now be collected by heat pumps or condensing boilers, or the boilers that will take maximum advantage. The chamber identification is, I suppose, important in your understanding of the manifold, but as such the manifold is a complete device, and when it's mounted on the wall nothing changes inside. There are no moving parts, nothing to go wrong. The system is designed to work, and it does work extremely well. Inside the manifold you have a flow deflector. What this means is that when water flows in from, say, the left hand side through L1, it hits the center of this V-shaped baffle, flows in front of the baffle and behind the baffle, and therefore is deflected away from this pipe. So the water coming from the left flows from left across to the right. If, on the other hand, the water flows in from the right hand side, it comes through, hits the deflector baffle in the center, turns back on itself and heads back in the same direction. So whether water arrives from R1 or from L1, it will always flow in this direction. Excuse me. In doing that, it will pass over these chambers here. This shelf here will cause it to be not in any way inadvertently drawn down into this flow, causing that zone maybe to heat when it shouldn't. And these also deflect the water outside those zone pipes here, zone flow pipes, so the water simply flows through, around and back. The boiler's only job therefore is to get water through the unit and back to itself. The boiler's pump only job is to do just that. The boiler pump has nothing whatsoever to do with the distribution of the zones. When water arrives into the system first, it's going to have air in the system, there'll be air trapped in the zones and radiators and whatever, and as the system starts to fill and you start to move air through, all the water carrying the air will be collected in here, and the air will rise to the top, and as it does, it's brought past this kind of air trap that's created, where it's deflected in towards a central venting port. T1 are the ports on top, T1 on the left hand side, T2 is the venting or expansion port, and T3 would be a cold feed or return port, depending on how you use the unit. I'll explain that in a while. The deaeration device also includes an obstruction at the back, purposely put there, so when water is flowing across, it causes a turbulence just here, and any air is broken up and finds it easier to rise and out of the unit. So therefore this simple little device here will deaerate the system extremely simply, very easily and very quickly. In the meantime, any water passing on will have to pass this chamber or this port. The distance between this port and this port is about 75 millimeters or 3 inches. Therefore the pressure differential between here and here is practically zero. So if there is any water pressure here, and this is an expansion pipe, and this might be a cold feed pipe into the system, there's no way a system can be would cause it to pitch around, because the difference in pressure between the two is not worth talking about. But we deal with that a bit more better later on in this presentation. So the boiler bypass chamber would say that if you have, say, 100 litres of water travelling through the chamber, some portion from this side, some portion from this side, and just suppose the first zone is taking 30 litres and second zone is taking 20 litres, well, that would mean there's only 50 litres gone. If this port isn't working, then the remaining water, the remaining 50, goes down and goes back to the boiler. The water having travelled through the zones also goes back to the boiler, but having delivered its heat. The zone returns are all collected in the zone return chamber. So any zone, if water did come in, say here 100 litres of water come in and is passing through here, and 25 passes out here, 25 comes back up here. If 35 pass down here, 35 passes up here. So therefore between zone 1 and zone 2 you have, say, 60 litres. If 60 litres collect here, and there's 100 litres came through here in the first place, then 40 litres will go back to the boiler's original location, and the other water can either flow back to the boiler's original location or be diverted to a cooler boiler, depending, again, you'll see in a while how the system operates. If we want to introduce, say, an oil boiler onto the manifold, we would very simply take our oil boiler flow connections and our return connections through a pump. Pump would be located on the return and would bring the unit into play by taking the coldest water from the cold return chamber through the pump and down through the boiler, heated again, back up outside the deflector plate and around, back down again, down through this bypass, back to the, say, condensing boiler. So therefore the boiler's path is very simple. The boiler's work and functions very simple, and of course the deaeration device, which we'll talk about later, will make sure that the system is perfectly clean of any air. If we add a zone, say for instance this was a pump and a non-return valve on a circuit heading off to, say, some radiators or a towel rail circuit or an underfloor heating circuit, depending on what you're doing, and let's say the second zone is going to be for maybe upstairs bedrooms heating of some description, you can attach whatever type heating system you wish to those. And then we would put in, say, if it was a sealed system, a pressure vessel. Because we're not using this port for the boiler, it's a very opportune place to locate a pressure vessel, because it has access to all of the water that's being heated, and therefore will create the perfect location for a pressure vessel. If on the third zone we put in a hot water cylinder, you might note that the non-return valves that are fitted on the returns on the zones are located directly onto the unit. But always and ever, if a hot water cylinder is used, whether it's with an NRG ZONE or any other system, it's always a very good idea to put a non-return valve as the connection to your hot water store, so when heat goes in, it's not going to drift back out and be lost by insulation losses when there's no need. The non-return valve is a very cheap, energy effective measure that will contain the domestic water within the domestic water container. When the pump is on, the gate opens, the water fills. When the gate is closed and the pump is off, the heat can't come back out. If, for example, we now want to add an open system stove to the equation, we simply put the stove at a given side, and then of course we're going to need an open tank. If we're going to put in an open tank to take the system water, store the head of water, we don't necessarily need the pressure vessel, although a pressure vessel here will do no harm. In some situations it's even advisable, depending on the run of pipework and any strange reason that might say the boiler should also have a little bit of protection from a pressure vessel. But normally speaking, you just have an open tank, your hot water cylinder with a dual coil, one heating from your boiler, oil boiler or a gas boiler, and the other ready to take heat from the stove. With the stove, we take a primary circuit, typically 1-inch pipe. Depending on the size of the stove, might have to be bigger. What you might note is a very good practice is that as quickly as possible after you leave a stove, you cause a gravity rise. The pipework should rise and rise vertically as quickly as possible, so that you get a thermosiphon started, so the heat will leave the stove without the potential of a pump interfering. As a matter of interest, this pump seems to be on the gravity circuit, but it actually isn't, as you'll see in a while. On this stove return there is an injector T, and if you look at that T, you'll see that it has a reducer inside. So you have, say, inch pipe or 28mm pipe, 25mm pipe feeding down in, and where this fitting might be, you can purchase injector T's, but you could also take this T a fitting, a reducer, and instead of having it come up here so you'd have a reduced size pipe into it, you would cut off most of the part that would be the slip into this fitting, turn the fitting, the reducer upside down, put it into place, mark the center of the connection at this point, and then cut it and then reinsert it back into the T, put your pipe in behind and maybe solder the fitting if that's a solder fitting or compression fitting or whatever is necessary. But you end up with a situation where this is now an open circuit back from the cylinder and the injector through the pump is firing water down, creating a venturia just here. In other words, a vacuum will be created here when this pump is on, pushing water down through the system. So you remain with your open primary circuit, as you'll see, but you also now have a pump assisted secondary return. So the return pipe coming from your hot water second coil, primary coil in the cylinder, has now an open path from the boiler up through the primaries, down through the coil over here, an absolutely open path down through to the stove. Extremely safe system. So now you see it more in context, in that you can see that the heating tank will have filled with water when it's connected properly. Cold feed leaves the tank and goes down, and we'll look at this area underneath better in a second. But the expansion pipe, where this pipe rises up as high as possible, goes across, vents any air in the system out into the expansion pipe, and then the primary water drops straight down through the coil, through the primary return, through the injector T with no obstruction, and down to the stove. So the stove has a perfect open path and will work perfectly even if there's a power cut and the pump is not drawing heat away. Of course, if the power cut is for an extended period of time and the cylinder starts to heat, your expansion will come into play and allow steam or expanding water to be taken away into a safe area within the tank in the highest point in the system. Now, you'll also see that we have a non-return valve fitted here on the cold feed. It's a cold feed bypass. This is the actual cold feed, and you'll see in a while it goes down and loops underneath and up into the system, so you don't cause any temperature to rise up along this pipe and heat the contents of the tank, which would cause the contents of the tank to evaporate, and therefore fresh water would keep filling in and the system could potentially rust from the inside out. So, but this here, a non-return valve on a T from the expansion pipe fitted just below the water level in the tank, means that the water, if water ever finds any reason to pitch and it starts to move up the pipe, it'll put weight on the gate of the non-return valve, which pivots on a nut just here. The flap in the valve will open, the water will fall down, and it will equalize the pressure in the expansion and cold feed, and you won't have any pitching over in the tank. So it's a very simple, very straightforward way of having a system operate safely without pitching. Again, I'd ask you to note that the water valve, if the water level is in the tank is at this height, the valve should be just below it, maybe 1 inch or 2 inches just below the water level, but at the same time in a position that if water starts to build up on the expansion pipe, that it will drop down and fill back in underneath. Let's have a look below. Below you see that the cold feed comes down, loops around and loops back up into the primary return. Where it loops back up, this pipe here will actually cause it to, with the cold feed coming down like this, it'll give it an opportunity to cause a heat lock. So if we zoom in to that for just 1 second, you'll see the hot water will not be able to go back down and push the cold back up here, so it'll be trapped inside here and will just carry on its own path. Whereas the bypass pipe coming from the expansion pipe above can come down and join into that pipe. So again, that can't feed back up into the expansion tank, but it can provide a bypass for any water that might be building up in the expansion. So that's the sealed system, or the sealed gas boiler system shown, and now we've looked at a solid fuel interconnection. But let's look If we decided instead to use the same energy zone unit, but we want to change the system completely and we want to put in a heat pump. So the heat pump, one way of installing a heat pump would be with a heat pump exchanger or a condenser. The heat pump itself will be collecting heat from the air outside, and we won't talk about that just now, but it delivers hot refrigerant gas into a heat exchanger inside. In turn, there's a plate exchanger inside which will convert that heat from the refrigerant gas into heated water, and a pump will pump out of here and up into the manifold. Let's have a look. So you'll see that the heat pump exchanger has 4 entry points: hot gas in, hot gas out, or cooler gas out having left the heat inside, and then a flow out of the heat being collected and a return back from the system, return going back in. If you look, when the heat leaves the heat exchanger, you could go about the system in this way, although it's not essential. It's a very useful way to take maximum advantage of a heat pump. The heat leaving the heat pump travels through the flow from the heat pump exchanger and arrives at this T. In option number 1, it can go through this valve if it's open and feed directly through the pipe inside the unit into the flow chamber and provide heat for the zones, or whatever zones are calling. The return, of course, would go back, having come back from the zones, will be the coldest possible water, and so the heat pump will have the coldest opportunity to collect the coldest water in the system. Although this may be a condensing boiler over here, you would still take it from the higher return temperature, because at the very least, and the very most it can get if the heat pump is on, is the output temperature from the heat pump, which typically will only be about 50 degrees. So if the flow is on in the second option, this valve closes and this valve opens. So you now see that instead of the water flowing directly into the manifold, it in fact goes through this valve and into the bypass chamber and moves across the bypass chamber directly, without passing the zones, into the return of the other boiler, which heats it, brings up to full temperature. So if this was a condensing boiler at this side receiving 50 degree water, it's going to condense extremely well. If the water leaving here is at 70 or whatever temperature you want, then the flows will take that away and heat your zones. The return water coming back will have dropped down below to whatever temperature is necessary. If it's within the boundaries of the heat pump drawing the water away, then this circuit takes it back through the heat pump and back out here again to preheat the other boiler. And if the heat pump is outside of its temperature range, a temperature sensor, which can be located here, which we'll talk about in a while, cannot allow the heat pump to fire, and instead the water will simply go up here and be taken back to the other boiler, to the fossil fuel boiler. So therefore you can have heat pump directly, or heat pump preheating the other boiler, or you can have a second boiler heating and not allowing the heat pump to run. So the overall system is again extremely straightforward. You've got heat pump delivering the refrigerated heat, the heat pump condenser taking the flow and deciding, do you want to heat directly out to the system with it, or do you want to preheat the other boiler, or will the other boiler just feed indirectly? Extremely straightforward again. One of the advantages of a heat pump is that you are in a position to use night rate electricity. Night rate electricity is typically about half price. If that's the situation, it would be very wise to consider storing energy that you would create during the night in a buffer. This is a very innovative and unique way of storing that heat, in that the buffer can be used to collect heat, and it can also be used as a zone input, because if you remember, we had an opportunity to bring heat in at the top port here as well, which we'll look at in a second, but we can also take the coldest water down and through this pump into the buffer. So if the heat pump comes on during the night and is delivering, say, 50 degree water across here, that water can be picked up here, taken down through here, into the buffer and it fills down, and the reason it does is that this valve will open and pull the water up along and have this water go back to be reheated by the heat pump. In that situation, the buffer valves come into play, where this pump pumps the water down, and therefore this pipe will deliver the heat out, and this pump will pump the water up, and therefore this pipe, the same pipe, will collect heat inside the buffer. So we've got a very useful way of making a decision. Do you want to use the heat in the buffer, or do you want to store heat in the buffer for whatever reason? You can see, so when this valve opens, the auxiliary wiring within the valve is typically used to turn on this pump, and when this valve opens, you turn on this pump. If this pump is on, it pumps out and therefore pulls heated water in, and if this pump is on and this valve is open, then it pulls cold down and pushes the hot water out. So because this pipe rises up from the manifold and travels across, it's a good idea to put a manual vent over here. Maybe you might decide to put an automatic air vent. I prefer to think a manual vent, because at least the unit itself will have eliminated all the air in the system in any case, and there'll be no need for a manual vent here. The aeration device within the NRG ZONE manifold is extremely efficient. So what we have here is yet another simple way of showing how to construct what would otherwise be a very complex system. But as you can see from this example, it could not be more straightforward. You have, say, condensing gas boiler and a heat pump with a buffer tank. Very simple connections. This information has been brought to you by Energy Awareness, always behind good technology. Hopefully you enjoyed the presentation.